welcome to the House of ZK Radio, which is a focused podcast and media channel exploring everything ZK, zero knowledge. I'm Alice, education lead at ZKM. Today I'm joined here with co-host Pavel, who is DevRel lead at ZKM, and our guest Niall, co-founder and head of GPU engineering at Snarkify. Thank you so much for being here, Niall. We're very excited to have you here today.
Hi, everyone. It's great to be here. Thank you so much for inviting me to your podcast.
Yeah, thank you. And I'm wondering, Niall, if we can first start off with an introduction about yourself and your story on how you got involved into the ZK spaces, and then your focus now specifically on hardware acceleration.
Okay, sure. Let me spend a minute giving an intro. So many moons ago, I did my undergraduate work in mathematics at the University of Massachusetts. When I got out of my undergraduate, I started a small software company, which was called Yrrid Software. And I did that for like 15, 20 years. Me and my housemate from college, we built software for the next computer. And then at some point that kind of started to peter out, and both of us wanted to go on to different things. And I had always wanted to go to grad school. Since I was living in a university town, I went to see one of my old professors, and he's like, yeah, sure, come show up in my office hours and we'll write a couple of papers. And then if you actually like doing research, then come and join the PhD program. So one thing led to another, and I joined the PhD program, and I was hunting around for projects. And I think about that same time, GPUs had started to become prevalent in terms of GPU computing. And I started doing work on big number algorithms. So we published a couple of papers in 2010 and 2011, and then I joined the PhD program in 2012, and I did that until I think I graduated in 2018. At that point, I joined NVIDIA as a dev tech, which is sort of their team that develops GPU kernels day in and day out and does a lot of the heavy-duty optimization of the kernels. And I was with NVIDIA for something like 5 years, and after that, the ZPrize came out. And I was thinking, wow, here's an amazing opportunity for me. Like, I have all of this skill that's exactly related to the ZPrize. You know, there are all these competitions out there. Like, there are these math competitions, there are these physics competitions. And it was like the ZPrize one was custom made for me. You know, it was like I had exactly the right skills to take a whack at it. So I left my job at NVIDIA. There was no way that I could stay at NVIDIA and enter the ZPrize competition. And so I've done that for, I guess, the 2 ZPrizes so far, the 2022 and 2023. And then after that, at the end of this past March, I joined Snarkify as a co-founder and the head of their GPU engineering. So.
Yeah, great. Thank you, Niall. And really nice journey how you first started with your initial interest while doing your undergrad, and then going to your PhD program, and then joining NVIDIA, and then finally to ZPrize and Snarkify. So really great journey there. Wanted to also ask you a bit more about ZPrize in particular. You've won quite a few categories across all different kinds of tracks, from what I remember, like the GPU, WASM, FPGA tracks. Wondering what are the main takeaways that you had from there, and what you believe is really needed to accelerate ZK proving?
Yeah. So okay, but let me start by saying I'm going to be a little bit of a politician, and let me apologize up front for that. So you'll ask me a question about economic inflation, and I'll tell you how great it is to go scuba diving. So let me just say, there are tons of these questions where I'm going to take the conversation in a slightly different direction and maybe answer a deeper question. And maybe some of the questions I don't really have the right skill set to answer. Okay, so that's just as an introduction, and let me apologize up front for diverting the conversation here and there. I think the ZPrize things, the fundamental thing you have to do really well to win the ZPrize is understand how your particular algorithm that you want to implement is going to map to the particular hardware. And in WASM, there's a particular runtime environment that you're running in. On the GPU, there's particular runtime environments. And so I want to take a look at perhaps one of the competitions, is Prize 1B. And there's something really interesting here from the results. So Prize 1B is the end-to-end proving. And on the side, I have a slide here which shows the results from the different teams that entered Prize 1B. And it's kind of surprising. You might think that that all of the competitions are going to be really close, that all of the teams will have performance numbers that are like right on top of one another. And when you look at these, you can see that there's this huge gap. So for example, the baseline code runs in almost 500 seconds. There's a submission at 50 seconds, then one at 32 seconds, one at 3 seconds, one at 0.7 seconds, and our submission at 0.55 seconds. And the speedups range from 8 times faster to 800 times faster. So this is something we also saw a lot at NVIDIA, where you would look at these academic research papers and there would be one that would come out, and then there would be another one that comes out that shows, hey, we're a little bit faster, and then another one that comes out and that's faster than the previous one. And you want to ask sort of a fundamental question, a computer sciencey question. Like, what is the fundamental limit of how fast you can compute some of these things, right? So how do I know, for example, that there won't be a submission that's 10 times faster than my submission? And I think this is a really important question to think about. And I think that maybe a lot of people in the ZK space haven't focused enough on this kind of question and how you can answer a question like this. So I want to spend at least a few minutes and try and talk about that. So when I joined NVIDIA, like I was saying, they focus a lot on what they call the speed of light. Okay, so you have some computation that you want to do on some kind of machine. And it doesn't matter whether it's a CPU or a GPU, an FPGA, or an ASIC. Again, it's always like there's a computation that you want to do on a particular piece of hardware. So one approach to finding this kind of lower bound of how fast something can be computed is to do the following. Let me change slides here. What you can do is you can take a look at what your actual algorithm needs to do. So here's a very hypothetical example. Let's say I have an algorithm that needs to read and write 5 million bytes of data. Okay, over here, let's say it needs to do 6 million additions, 2 million multiplications, and 500,000 divisions. Okay, now you run this on a machine, and the machine has these sort of theoretical throughput numbers. Maybe it can do 10 million reads and writes, bytes of reads and writes per second, maybe 10 million adds, maybe 5 million multiplies, and maybe only 100,000 divisions. So now, if you can overlap all of these operations, you can sort of think of it like, how long does it take to do my divisions? How long does it take to do my reads and writes? How long does it take to do my additions? And what you'll find is that the thing that takes the longest in this very hypothetical example is the divisions, right? So if we look at this, if we're doing 100,000 divisions per second and we need to do 500,000 divisions in total, the absolute fastest we will ever be able to make this computation work on this particular machine is 5 seconds. Now, and that requires a lot of fancy software even to hit that 5 seconds, because all of the other operations that you're doing have to overlap perfectly and run sort of in the shadow of the divisions. But this is a nice way to get like a lower bound on a computation, right? And so if you know these lower bounds, then as a team entering something like the ZPrize, you can sort of know that your solution is not really hitting the mark, right? That there's a lot of space for you to still optimize your submission. And I think if people had understood this kind of this idea of a speed of light analysis, then you could avoid some of these cases where people are so much slower than the optimized solution could be. So I'm sorry, I've taken us on my first sidetrack. I don't know if I've actually answered the question you asked, but I hope this has been an interesting diversion.
From there, I think that since we're on the topic of ZPrize, I'm very curious to also hear about the Snarkify's team approach to the track 1B. I believe for that track, the main objective was end-to-end proving of a Merkle tree on the GPU. I'm wondering if you can shed some light onto some of the design decisions, the approaches that you took, maybe some trade-offs that you had to consider during your implementation.
Yeah. So the Prize 1B project, we were given a very specific task, right? So there's a proving system, the ZK Garage, and it was used in a prior ZPrize to find out what the smallest number of constraints that could be done to prove one layer of a Merkle tree. And so this end-to-end ZPrize was you're given a much bigger Merkle tree, and you weren't allowed to make any changes to the proof system or the constraints. It was strictly a question of how you optimize the execution of this on the GPU device or an FPGA device. That was what we were given for Prize 1B. So we didn't have to do much experimentation with like changing constraint systems or proof systems. All that stuff was set down. And what that meant is that there was a particular set of computations that you had to do. And then the goal just becomes, how do you accelerate those particular computations on the GPU? And there are a couple of ways that you could approach this problem. So, for example, you could do a sort of a hybrid solution where you have the Rust code running on the CPU, and what it's doing is sending data over to the GPU, and the GPU runs some algorithm like an MSM or an NTT, and then sends the results back to the Rust program. Now that's certainly the easiest way to accelerate the original Rust code, but it turns out that it's not a terribly efficient way to do it. And maybe I could show a slide of the GPU architecture and explain a little bit more about why that's the case. So here we have a host machine. Imagine that this is running the Rust code. And if you want to do an NTT, for example, what you'd have to do is send the data for the NTT over to the GPU. The GPU would then run the NTT at a very high speed. I think it's worth noting that the PCIe bus, where you have to send this data over to go from the host to the GPU, is very slow compared to the rest of the buses in the GPU. The PCIe bus is like 20 gigabytes. So it turns out that you're going to spend a substantial amount of time moving data across that PCIe bus in comparison to the amount of time that it takes to process it on the GPU. So the takeaway from this is that you don't really, if you want to get a super optimized solution to the ZPrize, you don't want to be sitting in that environment where the host is sending the data over to the GPU on an operation by operation basis. What you really want to do is move as much of the proof system over to the GPU as possible, so that basically the data is constructed here already in the GPU, and then it remains in the GPU, and then only answers are sent back across the PCIe bus to the host. And I think that was probably the main decision that we had to make, was to basically break away from the Rust code and try and implement the entire proof so that it would run on the accelerator card. And I think there were other people that chose the same path. I think I'm sorry, I can't remember the team name. Let me just read it off. It's the Voronov and Kolganov, the second place finisher. They did it pretty much the same thing. And I think the key distinction between our submission and their submission was that we just had slightly faster fundamental operations. So our NTT was a little bit faster than theirs, and there was a couple of other places where we were quicker. I think that's the main takeaway, right? Is that you want to move as much of the proof over to the device as you can, and you want to break away from having the host be a significant part of the computation.
Yeah, thank you, Niall. I think a lot of people have the question on, oh, why is it really necessary for us to do the processing from the GPU? Why is that a lot faster? And yeah, I really appreciate you for showing us this diagram and for showing us how like the PCIe bus as that channel for moving data is pretty slow compared to the other buses. And I think that explanation was really nice and really detailed. So appreciate you for that. And also wondering, in terms of the approach you guys took in optimizing for the proof system, I saw that there were some particular parts that you decided to remove for your implementation. So I was wondering about the reasoning and the thinking for this, and what particular parts did the Snarkify team decide to remove?
Okay, great. Yeah, so the thing about the ZPrize is that it can be pretty difficult for one person to do an entire submission. So in fact, in all of these cases, we used teams of people. So there was, on my team, there was a person who was an expert in the proof systems, and he went through and he basically analyzed all of the gates and features that were used in this in this Merkle tree circuit, and he realized that, for example, the lookup gates were not required. And he also noticed that several of the polynomials that could potentially be variables were actually constant in this particular circuit that we had to accelerate. So what he was able to do was basically remove those parts that weren't used. He was able to remove the lookup gates. He was able to remove a bunch of the arithmetic gates. He was able to remove a lot of the constant polynomials. And so then what we were actually computed was sort of the minimum stripped down stuff that was needed for our particular circuit, and nothing extraneous to that. And again, I'm not an expert in the actual proof systems. My expertise lies in sort of optimizing the GPU code and sort of the architecture side of things. So I rely on other people to tell me what to take out and what we can shortcut.
Got it. So there was some like lookup gates, some arithmetic gates, some constant polynomials that weren't being used that you decided to remove.
Yeah.
Okay, got it. Yeah, thank you. Also wondering if you could give us a walkthrough of the proof generation process, specifically of the different proof rounds that were made and some of the interactions between the host and GPU for Snarkify's implementation.
Sure. I've put some slides in from a talk that I gave at ZK Hub in Thailand just recently. Okay, let's see. It's been a little bit since I gave this talk, but let me go through it with you. So there's, like I was saying, there's sort of two parts to the system, right? There's some piece that stays on the host that is used to launch the rounds on the GPU. So we have this kind of host processor. These are the things on this line on the left are running on the host processor, and these things on the right are actually running on the GPU. And the crossing points is data that we need to move from the host to the GPU in order to do the proof. So we start out with this initialization phase here. And there's a whole bunch of data related to the prover key, which is generated on the host at startup time, and then it gets copied over one time to the GPU. And then when a proof comes in that you want to actually go proof, the first thing you do is you just copy over the Merkle tree. Once the Merkle tree has been copied to the GPU, now we can start the actual heavy-duty math processing. This is where basically all of the heavy-duty large data objects are created and built for the proof. And the first step is witness generation. So here, basically, we have to fill out the trace table. This trace table is sort of the basis for all of the polynomial operations that we're going to do later on to actually generate a proof. So that gets generated in round zero. Then in round one, we do commit the witness, which essentially means we have to run some MSM operations. This is, again, a Plonk style proof with zkGarage as the underlying implementation that we're emulating. And we have to do a bunch of INTTs and a bunch of MSMs. When that's finished, then we can send the commitments over to the host, and there's a transcript object. The transcript object is sort of this I don't know, it's like a hashing object, and we didn't want to implement that on the GPU. And because there's such a small amount of data that comes over in these commitments, it made sense to rewrite as little code as possible and leave this part on the CPU. So the points that come out of the MSMs, these get committed to the transcript, and then we go on to the next slide. So you'll notice that in the previous slide we finished round one, and then here we start with round three. And it turns out that round two is completely related to lookups. So we don't actually need to run anything on the GPU for round two. That could be completely removed because we don't use lookup gates. On round three, there's challenges that get generated by the transcript object. Those get sent over to the GPU. So these are like the alpha, beta, gamma. I think there are a couple of other challenges as well. And on the GPU now, we're ready to do the next phase where we construct the Z polynomial. Then we do one INTT and one MSM, and we send the commit data back to the transcript object. And again, we do the next round 4A. Challenges go over to the GPU. We compute the quotient poly. There's cosets, INTTs, MSMs. The commitments go back, and then we get to round 4B. Challenges go over. We compute the linearization polynomial. We get these eval polynomials. The evals get written to the transcript. And it's just kind of this back and forth process. And then finally, the last round is round 5, which is these openings. And we do 2 quotient divisions and 2 MSMs. And finally, those get written back to the transcript object. And now the proof, essentially all of the elements of the proof are in the transcript object, and they can just be dumped out. And this whole process from round 0 through the end of the transcript runs in 0.55 seconds. So it's really fast. I think that is it.
Yeah, thank you, Niall. Very good to see those interactions between the host and GPU, the way that you mapped it out here. So yeah, thank you for showing us that. Also curious to hear, and this is related to another ZPrize category that you've done. I know that you incorporated an MSM technique that was used in a previous or another ZPrize category that you used. I believe it was ZPrize 1A. I'm wondering if you can give a walkthrough of that MSM technique that you developed, how it may differ from other methods from computing MSMs, and also if you can give a brief explanation for our audience who may not be too familiar on why optimizing for MSMs is important for ZK proving.
Okay, great. Let me start with the last part of your question first. I think that's be interesting. So I wanted to show a slide. This is a bit of an explanation of where that time went of that 550 milliseconds to do a proof. So basically, there were 6 steps that we saw, basically interactions between the CPU and the GPU. The first was witness generation, then round 1, all the way up to round 5. And I wanted to show you kind of a breakdown of the amount of time that was spent in each round. And so it was sort of 2 milliseconds for witness generations. That's really quick. 112 for round 1, 35 for round 3. And then the big one here is 317. So most of the time is spent in round 4. Then 3 milliseconds and 67 milliseconds. And then we can look by operation. So this is sort of telling you, if we look at this inverse NTTs, for example, there were 5 inverse NTTs run in round 1. There was round 1 in round 3. And this is the amount of time that a single inverse NTT takes. It's 1.23 milliseconds. So it turns out that if we look over here, the expensive operation in this proving system was actually running the MSMs. So if we look here across this, there were 4 MSMs in round 1, 1 in round 3, 6 in round 4A, and then 2 in round 5. So in total, there were 13 MSMs that were run, and each of those MSMs took 28.4 milliseconds to run. So I'm going to try and do this in my head. It's something like the total time for running the MSMs is something like 360 milliseconds. I'm sorry, I don't have a calculator in front of me, so maybe that's not exactly right, but it's something in that neighborhood. So out of the 550 milliseconds that it took to generate a proof, 360 of them were spent just running MSM. So this is the reason why the ZPrize people in a lot of the earlier competitions had been focusing so much on accelerating MSM. Since so much of the proving time is spent computing MSMs, every bit that MSM gets faster, that comes directly off the proving time. Let me give you a further example. Let's say you improve the quotient polynomial computation by 200%. It becomes twice as fast, right? The most time you're going to save is less than a millisecond, right? But if you can knock 10% off the time for MSM, you're going to save 36 milliseconds on the total computation. So MSM is the biggest and juiciest target for doing optimization, which is why so many of the ZPrize competitions have focused on it. So there was an MSM on the first ZPrize. There was the first ZPrize competition was 2022, and there were a bunch of submissions there, and sort of my submission tied another submission by Matter Labs, and a lot of ground was broken in that first MSM implementation, right? So those were very highly optimized. So by the time that this second ZPrize came about in 2023 for track 1A, there wasn't so much new ground to break in terms of optimizing MSM on the GPU. But we did manage to find a few kind of new ideas. One of them is to implement like faster sorting algorithms. And you might be wondering, like, what does sorting have to do with MSM? And maybe I can take another one of my digressions here and go talk a little bit about how sorting ends up playing a role in MSM. But it turns out, like, in order to compute an MSM on the GPU, you want to sort some data. And so the big improvement in this track 1A was improving the sorting. And I think there was one other idea that we came up with, which sort of was published after the track 1A finished, but before track 1B started, which is this idea that the distribution of points. So I'm sorry, this is kind of down in the weeds, but let me see if I can give a high-level explanation. The algorithm that people use to compute MSMs is something called Pippinger's algorithm. And Pippinger's algorithm works by having a whole bunch of buckets. And what you have to do is you take your points and you add them to particular buckets. Okay? Now, the way that those points end up getting targeted to a particular bucket has to do with the scalars that you're doing under MSM, and the scalars come out of like a particular step in the proving system. So it turns out that the distribution of points into those buckets might not be uniform. You can end up with circumstances where some of those buckets have a lot more points than other buckets. And it turns out that when you go to compute those buckets themselves, the ones that have a huge number of points can really blow up the MSM computation. It can make it so that it is way slower than it should be if the points were uniformly distributed. So we published a nice approach to resolving this problem. Basically, you can guarantee that the bucket distribution will be uniform, and then you avoid this whole problem of some buckets having a lot more points than others. Okay, sorry, that was a little bit on the complicated side. There's a slide I'd like to show here, and talk a little bit more about these buckets. So as I was saying, when you're computing an MSM, the way you go about it is sort of like this. You have a scalar times a point plus another scalar times another point plus another scalar times another point up to scalar n times point n. These points are points on an elliptic curve, and the scalars are the scalar field. So a very classic example is BLS 12381, where the points are in they're an x and a y. Each x and y is in a finite field with 381 bits, and the scalars are basically 256-bit numbers. So the best approach to solving this is you do something called Pippinger's bucket algorithm, and the idea works something like this. Let's look at a small example here. We have S1 P1, S2 P2, S3 P3, up to S5 P5. And these things have to get added to particular buckets. So for example, point 1 has to get added to bucket 1, and point 1 has to get added to bucket 4. Point 2 has to go into bucket 2, bucket 4, and bucket 5. Point 3 is only going to end up in buckets 3 and 5, etc. So now, like I was saying, if you find a scenario where one of these buckets has a huge number of points compared to all the other buckets, that can really cause performance problems in the MSM algorithms. And that is going to be based on the distribution of these scalar values. So there was one solution that we came up with to resolve that non-uniform distribution of the scalars. And the second thing that I wanted to talk about is where sorting comes from. Okay, so now it turns out on the GPU, there are two ways we can approach this problem. On the GPU, basically, you're going to run lots of computing threads, and they're all going to work in parallel, right? It's a little bit different from a CPU. On a CPU, one thing is happening at a time. It's a very sequential kind of processing. On a GPU, you have lots of threads, and they're all running at the same time. So there are two approaches you could take to doing Pippinger's algorithm. You could assign like this S1 P1 to a particular thread, and this S2 P2 to another thread, and this S3 P3 to another thread. So basically each thread gets a point and a scalar. Now in that scenario, what has to happen is that thread 1 has to go load bucket 4, add its point to bucket 4, and then write bucket 4 back. But there's a potential problem. Remember that it's also running at the same time as thread 2, which is computing this S2 P2, and S2 P2 is also trying to add its point to bucket 4. So you can have these conditions where two threads are trying to update the same bucket at the same time. And that can cause all kinds of problems. And you have to prevent that. You have to create some kind of locking mechanism on each bucket that says that, hey, this bucket is locked, and if another thread tries to work on it, it has to wait. It can't work on it right now. And that locking mechanism causes a fair bit of overhead on the GPU. The GPU is not very efficient at these kind of locking schemes and doing this this kind of communication between threads that are on distant parts of the GPU. So the solution on the GPU instead is what we're going to do is we're going to make a list of all of the points and all of the buckets that those points need to be added to. And then we're going to sort that list, okay? And we're going to sort it by the bucket number. So essentially then what it says is we get a list that says we need to add P1, P4, and P5 to bucket 1. We're going to get another list that says we need to add P2 and P4 to bucket 2. Another list that says P3 and P5 to bucket 3, etc. all the way down. And now what we can do is instead of assigning points to threads, we can assign buckets to threads. We can say, okay, thread 0, your responsibility is for computing bucket 1. And then thread 0 can just go out and read point 1, point 4, point 5, and do those additions. And because the points are all read-only, they're not being modified at all, we don't have any conflicts where we need to synchronize between threads. And it resolves that synchronization problem. So it turns out that you're going to incur some overhead by having to sort these lists and sort the data, but you're going to save a lot of time because you don't have these conflicts between threads. And so that was the approach. And the sorting idea was actually first tried in the first ZPrize. So that was an approach that was used in the 2022 ZPrize. But in the 2023 ZPrize, we actually found a way to do the sorting slightly more efficiently, and that saved time on the MSM overall.
Got it. Thank you, Niall. So just as an overview, the reason why optimization is needed, you showed us that at least more than, for that scenario, more than half of the proving time was spent just on the MSM. From what I remember, around 360 milliseconds. Got it. And then one of the ways in which this is slow is because, at least for Pippinger's algorithm, the distribution of points into buckets is not uniform. But the approach that you took is trying to make that distribution more uniform, in which instead of assigning points to threads, which you mentioned could have some scenarios where there's two threads, for example, trying to update the same bucket simultaneously, you can directly assign these buckets to the threads.
Yeah, that's a pretty good summary. I guess just to for clarity, they're sort of separate issues, the uniform scalars and the sorting. The idea of making the scalars more uniform is just that if you have a situation where the scalars are not uniform and you don't do any sort of pre-processing of the scalars, then you can land up in a scenario where one of these buckets has a huge number of points in it. Okay, and just to sort of elaborate on that a little bit more, since a bucket is being processed by a single thread, right? If 10% of the points end up in that one bucket, then one thread is essentially adding a huge amount of stuff, and it just overloads that thread, and it never finishes. Or it takes forever to finish in comparison to how long it takes all the other threads to finish. So that becomes a problem, and basically by doing this process of forcing the uniformity of the bucket distributions, we can solve that issue of one bucket getting tons and tons of points in it. So it's separate from the sorting.
Got it. Thank you so much, Niall.
Sure.
I see. Yeah. Thank you so much for the clarification. And I also wanted to scope out a bit. We discussed a lot on the advantages for processing directly on the GPU. I'm just curious to hear any sort of trade-offs or disadvantages that this GPU implementation may provide, and how, in general, how GPU acceleration compares to some of the other approaches that we've seen, like with FPGAs, with ASICs, and some of the advantages and disadvantages between those approaches.
Great question. Okay, so the obvious answer on these things is that it's a lot more work, right? So the proof systems are generally written in Rust, and they use ArcWorks, right? And The disadvantage is that if you really want to move all of the computation over to the GPU, all of the work that would have been done in ArcWorks and in a library that somebody else wrote that you don't have to worry about as a developer, now all of a sudden you're going to have to bite off all of that work and implement it on the GPU. And the thing about the GPU is that it's harder to develop fast software on the GPU than it is on the CPU. On the CPU, you can kind of just blindly write your code and not really worry about the very fine details about what thread is accessing what data, and it's a much simpler environment to develop software on the CPU, and you can use a lot of high level software tools, and like you can use a rich class hierarchy. You can it's just easier to do things on the CPU certainly than it is to do it on the GPU. And it only gets worse from there, right? So the amount of effort to get something running on the GPU, you times that by 5 to get the same work happening on the FPGA. And again, like the FPGA faces the same problems that the GPU does. If you only use the FPGA to accelerate MSM and NTT, then you're still going to be biting off the PCIe data link that's slow to transfer all of the data across from the host to the FPGA. So the way to sort of get the maximum performance out of all of these accelerator devices is to try and get the entire proof system up and running on the accelerator, or at least let's say 95% of the proof system running up on the accelerator. And what that means is that you have to bite off all of the functionality that would have been given to you for free in ArcWorks, for example, that you never have to write it. In ArcWorks, you never have to write finite fields. You never have to write elliptic curve addition. When you go to one of these accelerators, you have to implement all of that software, and you have to do it in a way that's really careful and maximizes the performance of the accelerator. Okay, and then again, if we take that times 5 and we go to an ASIC environment from an FPGA, I don't know, it's probably like another times 5 in terms of the amount of work it is to get something running really well on an ASIC. So you can easily say that the amount of effort to get this stuff working on a GPU is like 10x less than an ASIC. Something like that. I'm just throwing around numbers, but something like that.
Got it. And there's it's interesting to see those different trade-offs that you need to navigate between those approaches.
Yeah.
Mhm.
And I would
Okay,
also say
great.
that like this burden of getting all of the functionality running on whatever accelerator you're using, it's a big burden. There's a lot of operations that are called, and each one needs to be planned out and developed. It's a lot of work. So for example, to get the end-to-end proof on the ZPrize, we had MSM finished as part of the first track 1A. It probably took us 6 months to get everything running on the GPU. And I was also part of a team that was trying to build the same thing on the FPGA, and we just couldn't finish it. And like the ZPrize for track 1B started in, let's say, the middle of March, and it ended at the end of September. So we had a lot of time, and there were 2 engineers working on it. We just couldn't get the whole proof system up and running on the FPGA in that time. So it's just, it's a lot of work. And this is just one proof system, right? So if we look at the ZK space, there's proof systems coming out all of the time, right? There's like the Plunky 2, Plunky 3, SP1, the RISC-0, Jolt. There's tons and tons of proof systems all the time. And trying to get all this stuff running is just a really tall order.
Yeah, absolutely. Yeah, thank you. Thank you for that. Um, Also wanted to go into the topic. I know that Snarkify is really pushing the narrative that GPUs should be treated as first-class citizens. And for ZKVMs, we see a lot of ZKVMs having the approach where they are first building on top of the CPU base and then optimizing for accelerators later. But for for you guys, you're really trying to push for building GPU native zkVMs. So building zkVMs that are designed directly for the accelerators. I'm very curious to hear some of the implications, some of the differences for this kind of GPU native zkVM over our conventional approach, and any kinds of new challenges or new opportunities that may be introduced with building GPU native zkVMs.
Okay, that's a great question. So let me start by saying that I think a GPU can accelerate any zkVM. So it's not let's say, for example, you take SP1 or RISC-0 or Jolt. You can take any of these solutions and you can get a huge acceleration by moving it over to the GPU, right? So it's not like I wouldn't want people to have the impression that you can't accelerate things that were designed for the host and then you want to run them on the GPU. That works great. Okay. The further answer to that question, though, is that maybe if we co-design, right? Maybe if we think about what are the things that the GPU really excels at, and we try and push the proof system in a direction where we're relying more and more on the operations that the GPU is great at, then we can even get some further acceleration beyond the other approach where it was sort of started out as a CPU implementation and then we wanted to accelerate it on the GPU, if that makes sense. So I think there are some opportunities there. There are a couple of things that are complicated on the GPU, like for example these questions of where multiple threads that are on distant parts of the GPU are trying to update the same data structure. That's pretty painfully slow. So maybe you can design your proof system so that it avoids that kind of scenario. Another thing I think that is really difficult is in a number of cases for zkVMs, the witness generation is kind of a serial process, right? So you know what that means is you've got some VM that's running a bunch of instructions, and you can't really parallelize that. Like those instructions have to be run in a particular order, and the ordering is super duper important, and you can't predict what some instruction will do until you've run all the instructions before it, right? So it's an inherently sequential process, and the witness sort of is an offshoot of the execution of those particular instructions. So it sort of implies that witness generation is a very sequential kind of process. Now, maybe it's possible to design different kinds of zkVMs where the witness generation doesn't have to be as sequential as that, or maybe there are some portions of the witness generation that can be parallelized. And so those are the kind of opportunities where if you do co-design between your proof system and your GPU implementation, maybe you can make some of those things a little bit faster than they would be by just taking SP1 and accelerating it on a GPU, for example.
Got it. So there's two different kinds of approaches that we could take here, like for example, accelerating a current zkVM, but there are some advantages in having that co-design between proof system and then also the GPU implementation. Okay, got it. Thank you. And also curious to hear about some of the longer term versions that we've been seeing in the space recently, like for example, snarkifying Ethereum's consensus layer, or achieving real-time proving. That's a main goal that we see within the ZK space, specifically within proving. I'm curious to see or to hear about what is really needed in order to enable those kinds of long-term visions and how GPU acceleration can contribute to this roadmap.
Yeah, I mean, great question. So the first point I think is pretty apparent, which is that if you don't have if you don't have some kind of acceleration, running these proof systems on the host itself is pretty slow, right? And you can see that just by the ZPrize results. The GPU accelerated version of the Track 1B ended up being 900 times faster than the host code. Now, let me just say that the host code wasn't very efficient. Some things are naively implemented in the host code. So maybe if somebody spent a lot of time optimizing the host code, maybe you could get it to be 5 times faster, something like that. But you're still, the difference between 5 times faster and 900 times faster is a huge jump. So what that argues for is that if you really want to Snarkify every block on the Ethereum chain, you're going to need some kind of accelerator to do that. And you're not going to do it on the host. So that's the role that I think GPUs, FPGAs, and ASICs play in that space. Is all three of those kinds of solutions can perform that acceleration. Now, I'm that during this talk we can get into some of those distinctions about why I think that GPUs are the right way to go instead of like FPGAs or ASICs. But I think it's the general answer to the current question is that some kind of acceleration is really important to get it so that the proofs come out in as near to real time as possible, because Ethereum is going to be producing a whole bunch of these blocks. Like another one comes out, it's every maybe 10 seconds now, and it's in the future they want to go towards every second. So in the ideal world, it would be great to be able to get a block proved in some close to real time. Maybe, I don't know, maybe it's a little bit optimistic to say you can do it in 10 seconds, but maybe we'll get there someday. So that's the goal. And certainly if you're doing it on the CPU, that's never going to happen.
Right. And I also wanted to ask you about some of the predictions that you have for the future of acceleration, specifically within ZK acceleration. You mentioned that we will see the GPU based approach dominating, at least for the next few years. But later down the line, do you still envision the GPU-based approach dominating, or do you believe that we'll have maybe some sort of hybrid approach combining multiple methods, like what you mentioned with FPGA, with ASICs, or just the GPU approach itself? I'm curious to hear about some of your predictions for what may happen later down in the line. And maybe here you can also go into some of the advantages, at least right now, that the GPU-based approach can provide over some of the other approaches that are being implemented.
Sure. What was the Yogi Berra quote that it's hard to predict the future? Okay, I still think that the GPUs for the next couple of years are by far the cheapest way to go, and there's a couple of reasons for this. The first thing is that there's a lot of flux going on in the proof systems themselves, right? So for example, we have a project where we're implementing SP1, and every time we try and decide on a version of SP1 that we're going to standardize on, guess what? There's another version halfway out the door. The changes are coming fast and furious, okay? And so now on the GPU side, the GPU is mostly a software platform, right? You write these kernels, the kernels run, they do their processing. On an ASIC, it is way harder. Like, you tape out a chip, the chip goes off to a fabrication, you don't get the chips back for, 4 months. The chips have to be tested, then they have to be put into cards. So there's like this good period of 6 months where you don't have a physical piece of silicon to actually even begin testing. And what happens to all the changes in the proof system during that 6 month period? That's certainly an issue. So if somebody's going to invest tens of millions of dollars doing a 5 nanometer ASIC, right? They're going to want a situation where the proof system is stable, and they're going to want to know which is the winning proof system, right? Like today, there's a bunch of proof systems out there that that could end up being top dog, right? The last thing you want to do is build an ASIC for $10 million that is for a proof system that nobody wants to use. So there's a lot of problems, just in terms of the changing of the proof systems and that kind of dynamic thing. Whereas in the GPU, we can like, let's say that we want to do an SP1 and a RISC-0. There's some commonality between the code bases between those things. You don't have to throw away everything you've done to support the two different proof systems if one turns out to be better than the other. And also with the GPU, is it the same GPU can certainly accelerate SP1 as to accelerate RISC-0 as to accelerate Jolt or Halo 2. So basically all of the proof systems can run on the same hardware. So that means if you make an investment of buying GPUs to provide cloud services, you know that investment is going to work across these changes. Okay, and I think that's one of the really important things for the short run. And then in the longer run, we were talking a little bit about at the beginning of the conversation about what tends to be the blocking factor. Let me go back to a slide here. So in this speed of light analysis idea, where we were saying that the most expensive thing in this really hypothetical scenario was these division operations, right? It turns out that when you start to look at proving, the most expensive thing tends to be not the computations on the finite fields. It tends to be the amount of data that you have to read and write. In other words, proof systems are memory bound. They're not compute bound, they're memory bound. And so what that is saying is that in order to get your proof system to run faster, what you need is a faster bus between the chip that's doing the compute and the memory. So I'm sorry, I'm jumping around slides a little bit, but let me bring up another slide again. So this diagram is sort of a high-level view of a 4090 GPU chip. It's like a consumer grade thing. But one thing I want to bring your attention to is that the bus speed between the GPU and the DRAM runs at 900 gigabytes a second. Now, the reason it's so fast is that GPUs need to do graphics, and graphics need tremendous amounts of bandwidth in order to run modern games. But we're piggybacking on top of that. So like we buy a GPU card that was meant to run graphics, and we get to do zero knowledge proving on it, and we get to make use of this whole 900 gigabytes per second bus. Okay, now the reason this is important is that let's say you replace this chip here, this GPU chip, with an ASIC chip. That ASIC chip still needs to connect to memory, and the performance of that ASIC chip is going to be dominated by the speed of this bus. And again, it doesn't matter whether the GPU is doing the computing or an ASIC is doing the computing. The thing that's going to control how fast proofs run is the speed of this bus. And the reason for that is because most of the zero knowledge proof operations are memory bound. They're not compute bound operations. I'm sorry, I know this is like a little bit on the technical side, but I think it's really important for the argument as follows. So it turns out that when you look at the cost of making a card that is going to go into a system, one of the factors is the amount of money that you spend on the memory and on designing this bus. And what I'd argue is that probably half of the cost of a card goes into the memory subsystem. So let's say that somebody wants to mass produce an ASIC. At most, they're going to be able to do it maybe something like twice as cheap as a GPU, even when they get to high volume. Okay? And there's this kind of rule of thumb that if you can't get to like 10x, probably an ASIC doesn't make sense. So I guess the kind of the longer term argument that I would make is that GPUs are going to be a cheap solution for a long time. And the reason is that the algorithms are memory bound, and that means you're going to need to build a really fast bus, and that costs a lot of money no matter how you cut it.
Got it. And thank you for mapping that out, Niall, and also for really differentiating that these proof systems aren't compute bound, but instead memory bound. So yeah, thank you for that, Niall. So all very clear. Also, just as a last question before we close up, I'm wondering if there's any sort of final thoughts or last takeaways that you have, or even if you have any advice to our audience that you would like to give. Just your final thoughts, maybe any announcements that you'd like to make before we close.
I don't have any announcements. Maybe I should have been thinking about that, but I haven't been thinking about that. Um, I have one other slide which I would love to show. There's another kind of seductive case for ASICs, right? So if we look back at the history of like Bitcoin mining, so Bitcoin mining started out on the CPU, then it quickly moved to the GPU, then it moved to FPGAs, and then the whole thing became absolutely dominated by ASICs. Like ASICs just crushed everything else that was running Bitcoin mining. And so people sometimes take a look at the lesson from Bitcoin mining, like it's cryptocurrency, right? Come on, it's the same thing as zk. And that's the wrong lesson. And I wanted to spend a minute just talking about why I think that's the case. So when you look at like a Bitcoin mining chip, okay, basically all it has to do is have a hashing engine which tries out different nonces and hashes them and checking for which ones have, a whole bunch of zeros at the end. And whenever like this hashing engine might run for days before it actually finds an answer that matches the criteria. But what that means is that all of these computations going on in all of these hashing engines are entirely independent. They never need to talk to each other. They never need to read anything off of memory. In fact, a Bitcoin mining chip doesn't even have like a memory bus off of it, right? And never mind 900 gigabytes, it has 0 gigabytes of bandwidth to memory chips. There literally are no memory chips. So what that means is that like you can make really inexpensive Bitcoin mining chips, and they can just completely dominate the picture because there's no memory bus, there's no communication, there's really simple to design. All you do is you make one hashing engine and you replicate it like 1,000,000 times on the chip, and then you're done. That's not the case with zero knowledge proof chips, right? If you're going to be making a zero knowledge proof chip, it's going to look a lot more like a GPU, and there's going to be a lot more intellectual property in that design. There's going to be a fast memory bus, all these other things. So I mean, bottom line, just to say it again, people shouldn't take what happened in Bitcoin mining as a predictor of what's going to happen for zk proving. Okay, then coming back to the question that I was supposed to answer, which is final thoughts. I have a couple of things that I think we've covered on. The speed of light analysis, I think, is a really important idea where you think about like what is the particular bottleneck of the machine you're using that is preventing your algorithms running faster. You should be constantly thinking about that. The second thing is that when you're thinking about algorithms, you have to start thinking about like how your algorithm actually maps to the hardware that you're running on. Now, this is something you generally don't think about with a CPU, right? With a CPU, you just kind of code out your software. But when you get to GPUs and certainly FPGAs and ASICs, you have to think about how your algorithms map to the computing capabilities that are in your device. Okay. Another major takeaway is I think that for people that are building FPGAs and ASICs, what you're going to end up with is an architecture that looks a lot like a GPU. You're not going to end up with an architecture that looks like a Bitcoin mining chip. You're going to end up with an architecture that looks exactly like a GPU. There's going to be a big cache in the middle of it. The cache is going to connect out to like tons of compute elements, and then there's going to be a giant, really fast bus. So in some sense, what what you're doing is you're trying to, you're trying to build a GPU essentially in these other environments, like in an FPGA environment and an ASIC environment. They're going to be analogous in many ways. And then the final major point is that the ZK algorithms are all essentially memory bound. I mean, the one exception to that is MSM is not as memory bound as the other ones, but I think most of the modern proof systems are trying to phase out MSM anyway, so they're becoming just more memory bound. So I think those are the big picture main points that I wanted to cover, and I hope I've done an adequate job and people understand the way I see this.
Thank you so much, Niall, for this very concise summary, and then also appreciate all of the insights that you brought from today's discussion, from the approach that you took with your ZPrize submissions, showing us why processing directly from the GPU is faster than moving data from the host. Some of the approaches that you took in optimizing your MSM implementation, and even some of the nuances regarding GPU native ZKVMs and why we shouldn't take the Bitcoin mining chip roadmap and compare it directly to designing ZKP chips. I think that was all very insightful, and really appreciate all that you've brought here today.
I want to say thank you so much for having me on your podcast, and thanks for the great questions. Like I'm really happy to be able to share some of these things. I hope that people who hear this find it interesting and get some value out of the view that we have at Snarkify about how things will develop in the future. Thank you so much.
Thank you so much, Niall. Thank you.
All right.